This conference will now be recorded.
Hello, everyone, to another session of TAP. So today we have a presentation by Orolia team with Stavros, John Arnold, and Christian Shori. So we'll start basically with a bio for each, and we'll hand it to them for the presentation. So Stavros Melachroinis, sorry if I
Melachroinos.
Melachroinos. I knew I will pronounce it wrong. I always have a problem with this Greek last name. It's very hard. So Stavros recently joined Orolia as a senior product manager for the atomic clock solutions. He's a product expert with several years of experience in position, navigation, and timing. He has worked several years with GNSS before joining the company. Stavros joined the Paris Observatory in 2003 and the CNES in 2004 to complete with honors a doctorate in geodesy and GPS networks. Stavros is a product expert with several years of experience in positioning, navigation, and worked on several years with GNSS before joining the company. This is repeated. I don't know why. Anyways, so John Arnold is a senior product manager. As a product manager, John Arnold helps Orolia's customers in designing custom PNT systems for multiple markets, from defense to critical infrastructure such as financial and data center. Prior to Orolia, John Arnold worked in pre-sales and product development for various security and aeronautic companies. He holds a engineering degree in electronics, and is a keen sailor. Nice. So last but not least, Christian Shori, an R&D product manager. Christian Shori joined Orolia in 2012 as a R&D product manager with a focus on miniaturized or miniature rubidium atomic clocks and advanced microwave ion clocks. He holds a doctorate degree in physics from Aarhus University in Denmark. So hopefully the screen sharing, everything is solved. Is it? So with that, with no further ado, guys, the floor is yours. Who goes first? Stavros?
Stavros, I think.
Yeah. Like we have the slides.
Presenter, you have a screen share button at the bottom. Okay, let's start differently. Christian, would you like to share the screen for everyone?
Christian, you're muted, so. Unmuted.
Yes, I'm unmuted now. So actually, so how do I share my screen?
I made you the presenter, and now you can share the screen for the rest. Here you go.
Yeah.
Can you switch to presentation mode? Perfect. Floor is yours.
So Stavros.
Stavros is, let's see if he's muted as well, I guess. Stavros, you're not muted. I think it's probably from your end. We cannot hear you.
Looks younger.
Okay. Still technical difficulty, I guess.
Okay.
We can hear you, Stavros.
Okay, perfect.
Okay, let's
So
start.
do I have the control of, because I'm having issues with my network here.
No, that's Christian sharing. Please ask him
Okay,
to change
Christian,
slides.
yeah, just go next, Christian.
Yes. I will stop sharing.
No, go ahead. Share your slides. It's better. I'm having issues with the network here.
Okay, very well. Can you see the screen,
Yeah.
Stavros?
Yeah, go ahead. Go to the next.
Okay.
Okay, so this is us. So we're going to present a couple of things about the Orolia atomic clock solutions, just for a very small bit of it. And then Christian will take over to go ahead with the principles and the functionality of the double resonance atomic clock, the mini rubidium that we have, the MRO50. And then it will go more in detail into its physics package, electronic package, and performance. And then at the end, we present as a use case the atomic reference time card by Jean Arnauld and the Orolia team in France. Go ahead, next. So a couple of things about us. Orolia is a global business in resilient PNT applications. The core of the mission is critical applications. And we, on our end, on the Neuchâtel organization, we provide the timing component. And Jean Arnauld can say a little bit more about the other business in the timing server and time cards domain. Next. Our Neuchâtel production is in Switzerland, of course. All production sites are on site. Here you can see a couple of photos of our burning labs, our space maser testing labs, and everything that has to do with temperature and industrial production, which is on site. Next. So just a couple of words about our niche markets, our verticals. So we mainly access to about 6 vertical markets. Those about timing and sync, defense and avionics, telecoms and broadcast, mobile systems, science and metrology. We have a very good tradition in science, especially with our atomic active masers and the passive masers, and the space domain, where we are one of the main providers of GNSS, the GNSS Galileo system. Go ahead, next. And as I said before, our tradition is rather large, spanning from ground applications all to the way to space applications. Our newest achievement is around the Galileo system. As you might know, we've been chosen to provide the next rubidium units for the second generation satellites, and we continue working on the passive maser unit, which will be also on board. We also had a couple of projects with the Indian Space Agency, ISRO, and BeiDou on the GNSS program. And here for comparison, we just superimpose the other 3 GNSS systems, the one from Japan, the QZSS, GLONASS, and Navstar GPS, for which we don't have a participation there. Next. Yeah. And our portfolio is separated in 5 main families. Those consist of the iSource family, which basically are rubidium sources, all in freestanding mode, and others with the capacity to be disciplined or not. Then we have the iSync family, separated in 4 main categories. Depending on the applications, we also have rigidized components in this family, and they are separated from the iSource family basically using on-board GNSS receivers, and also the disciplining function. The iSpace family is what I mentioned before. The crystal oscillators that we have are high-end oscillators, and the RAF's atomic standard, which is on board the Galileo standard satellites, and as well as we participate on the passive hydrogen maser unit, which is also on board the Galileo. In the IRF's family, we have rackable products providing reference sources mainly from Rubidio as well as VCXOs. It can have also in or on-board the GNSS receiver or not. And we also provide in this category the active hydrogen maser and the passive hydrogen maser for more precise applications together with T4 science. And the last category is the iTest family, where we provide femtomes, tempers, and picotime rackable units for high performance stability analysis or calibration. And next, I think, Christian, that will be the last of my slides, and I will pass it over to you.
Great, thanks, Stavros. So on this first slide, let me just say I will talk about the MRO50 product from Orolia, atomic clock, and but I'll start out a little bit theory. So on this first slide, just to recapitulate the basic principle of an atomic clock. In a single sentence, you can say that the clock is a local oscillator, typically a 10 megahertz crystal oscillator, which is disciplined to an ultra-stable atomic system. In block diagram form, shown here below, you have the crystal oscillator on the lower right hand, which gives the output to the end user. That megahertz oscillator is multiplied in the gigahertz range, and that gigahertz microwave signal is injected into an atomic system, generating a discriminator absorption signal shown on the upper left hand on the block diagram. Using some login detection, phase sensitive detecting, we can transform this absorption signal into an error correction signal, which is fed back to the crystal oscillator, thereby closing the disciplining servo loop. Also important to note is that the time constant of this servo loop depends on clock type. For the rubidium clocks we talk about today, it's typically a fraction of a second. And finally, the stability of an atomic clock is determined for short time scales below tau by the properties of the crystal, and for long time scales above the tau time constant is determined by the atomic system noise. So just to give you a short feel of the components in an atomic clock, to the right you see the MRO50 atomic clock from Orolia opened, and you can identify the key components for this servo loop that I discussed right now. On the left, you have the TCXO, temperature compensated crystal oscillator, which is locked to a 3 gigahertz VCO with an n-fractional PLL loop. That's the blue box on the right. That 3 gigahertz microwave signal is injected into the physics package, the orange box on the top. We will see what's inside later. And the loop is closed by a signal processing unit shown here in the red box. It's closing the loop and also doing the phase sensitive detection. Okay, so I would like to discuss the physics of the frequency discriminator signal. That's the physics package, the atomic system, where we use the technique of microwave optical double resonance or MODR technique to generate the frequency discriminator signal. So how does that look? You have a schematic on the lower left side, where an optical source, infrared source, is transmitted through a rubidium glass cell, and picked up on a photodetector. The rubidium atoms inside this cell, they have a level scheme shown on the upper right hand on the slide. And once the optical source is tuned to the optical transition between the ground states and the excited states, you get a broad absorption curve, an optical absorption curve. That's the purple curve you see on the lower part of the slide. And this absorption of the optical source in the rubidium cell leads to a phenomenon which we call optical pumping and state preparation of the ground states of the rubidium atoms. And the second part of the Doppler resonance method is injecting a microwave signal. Typically, normally, here, classically, if you want, by a microwave cavity surrounding the cell. And that microwave signal, when you look at the level scheme, will perturb the population in the ground state. And that gives an additional small dip in the optical resonance. And that's what you see in the zoomed image to the lower right part of the slide. You see on top of the optical resonance, you see a microwave resonance. So when the microwave source is tuned exactly to the clock transition between the ground states in rubidium, you get this frequency discriminator signal, which is typically a few kilohertz large and has a level of only 1%, typically 1% change of the light level on the photodetector. So historically, the size of rubidium atomic clocks is typically was determined by the size of the microwave cavity. So if you go back in time to the first, some of the first rubidium units, there were, as shown here, an HP rag unit from the 70s would use a quite large microwave cavity using the TE011 mode. And that could be realized with a big cavity of here 80 cubic centimeters. And as there was a progression towards smaller and smaller rubidium clocks, fabricants went by smaller cavities, for example, using the TU111 mode, which leads to a smaller cavity. And more recently at the Orolia, around 2000, slightly a few years before, we introduced a small microwave cavity LC magnetron of a few cubic centimeter size. This is actually the one which is used in our product, the SRO 100, shown here on the lower part on the graph, which has a size of 175 cubic centimeters. Now, what is the next logic step if you want to make the clock even smaller? It's to get rid of the cavity. And you can do that in either of two ways. Either you can replace the cavity by a simple microwave antenna, or you can use another interrogation technique called coherent population trapping, or CPT. So these two, I would like to discuss them and compare them because they are important for the function of the MRO50. You see on this slide is again a photo of the MRO physics atomic clock with the physics package, and now you see a zoom on what's it inside the physics package. You have actually on the left here the VCXO light source. It's a vertical cavity surface emitting laser, infrared laser, and in the center of this cat drawing in the upper right corner, you have the rubidium cell, and on the right you have a photodetector picking up the signal. We use in the MRO50 a quite small glass-blown wrapper cell, 5 millimeter outer diameter. And I would like to point out that the resonance that we're using has a clock transition of 3 gigahertz. The corresponding wavelength at 3 gigahertz is 10 centimeters. So that wavelength is much larger than the cell size. And that actually allows us to get completely rid of the microwave cavity, which would be much larger than the size you see here, and actually replace the cavity by a small loop gap antenna. And that's the cylinder which you see on the upper right corner. It's actually transparent. It's around the glass cell, so it's that cylinder around the cell, which is our loop gap antenna. And with this solution, we can actually produce quite small physics package of a few cubic centimeters size. And that technology is used in the MRO50 and patented in several countries. Now, the other solution I mentioned to get rid of the microwave cavity is this coherent population trapping, or CPT. In this case, as you can see on the schematic in the lower left part, there's no cavity at all. Actually, you are modulating the optical light source with your microwave source, and that generates a carrier with the two sidebands, just as in FM modulation. When we look at the level scheme again of the rubidium atoms inside the cell, now the rubidium atom actually sees on the upper left corner, you see this optical source it's modulated. You see the carrier with the two sidebands, and when the two sidebands are tuned into resonance with the optical transition from the ground states to the excited state, you again have a large optical absorption. That's the purple absorption line you see on the lower part of the slide. And now in CPT, what happens is that once you are on top of that resonance, at the bottom of that resonance, when you tune the modulation of the optical source so that the sidebands are exactly resonant with the two lower ground states separated by the clock transition, you generate a so-called superposition state between the ground states, which is a dark state. So some of the atoms in the rubidium cell are no longer absorbing the light, and that leads to a small increase in transmission of light through the cell. And that's what you see in the lower right corner on the right graph. You again see a microwave resonance, typically a kilohertz broad, and again with a small change of a few percent of the light level, and that's the CPT resonance used as a frequency discriminator in clocks based on CPT. So my conclusion and the last few slides, and what I would like to have you as a takeaway message from these slides, is that the microwave optical double resonance without a cavity actually allows to make a quite compact physics package, a few cubic centimeters, which is comparable in size to CPT solution, and is also comparable power consumption, can be comparable in power consumption to CPT solutions. Furthermore, actually, with this solution, we don't need to make a high frequency modulation of the VCXO diode, and therefore there's no requirement to stabilize the modulation index of the VCXO, which is quite a strong requirement on CPT clocks. Finally, there's no need also for the quarter wave plate. There's an optical element which is needed in a CPT, which is not needed in double resonance. So finally, of course, the MODR double resonance technique without a cavity does require an additional compact microwave antenna, but the fact that we reduce the size of the clock actually allows us to make a quite simple antenna for compact rubidium clocks. So these two methods are quite comparable in performance. Now I want to change gears and go to discuss an important parameter for the TAP project, the holdover performance of oscillators, atomic clocks, VCXO, etc. The time error, typically we divide it up in several terms listed here. The first two terms are time offset errors, frequency offset errors, so synchronization and synchronization errors. They typically will arrive if your clock is not well disciplined to the GPS source or master clock. The third term is quite important when you compare VCXOs to atomic clocks. That's it's a quadratic time error caused by frequency aging. The fourth term is just statistical fluctuations. That's the Allen deviation, for, say, at 1 day converted to a time deviation. And finally, the fifth term is time error caused by fluctuations in the environment, such as temperature variation, pressure variation, vibration and shock, etc. Since you have these power terms in the time error, linear and quadratic, it's useful to plot the holdover time error on a double logarithmic graph as shown on the right. That you have the time error on the y-axis and the holdover time where the clock is operating autonomous. To guide UI, I've plotted the two dashed lines. At 1 day, you have a 1 microsecond error. So if you take, for example, the purple line, that's the time error from a clock that has frequency offset of 10 to minus 11, typically what's the max frequency offset in a stratum 1 clock. And has a slope of 1. On the two other lines are aging lines. If we take first the red line, it's typically for an OCXO, you would have an aging, let's say, of 10⁻⁻10 per day, giving you already a time error of several microseconds at one day. You can compare that to the aging of a good rubidium clock, let's say with an aging of 5⁻⁻12 per day. Then you end up with a time error at one day of only a few hundred nanoseconds. So this holdover time can be used to compare atomic clocks, and this was done in a recent publication. You have the reference on the lower part of the graph of the slide. So this graph actually compares more or less all commercial available atomic clocks today, 2021. And it compares these clocks by comparing their time error after one day as a function of the power consumption of the clocks. The lower left corner is of course the best place to be, a low time error and low power consumption. But you see that you actually have the clocks actually line up quite nicely. In the upper left corner, you have typically rubidium clocks for ground applications, such as chip scale atomic clocks, miniature atomic clocks, classical double resonance clocks. In the center of the graph, you have rubidium clocks for space, and still a little bit more to the lower right corner, you have cesium beam tube atomic clocks, optical pumped cesium, the newly introduced gold rubidium clocks, and on the lower right corner you have passive mesons and active mesons with the best holdover times, but quite large power consumptions. Just a word on the MRO clock, so you can see where it's positioned in this graph. It has actually a quite low power consumption, below 1 power, which puts it closer to the chip scale atomic clocks, but still using a classical Weber blown cell and double resonance, we get quite good holdover time performance, which is comparable to miniature atomic clocks, which usually have 10 times more power consumption. So that gives you an idea of where the MRO is positioned with respect to other clocks. Okay, so let me show you 3-4 slides on the MRO 50, and first of all, I'll give you the specs. The MRO 50 is based on the Orolia rubidium clock design heritage, but adapted for low power and small size. The photo, you have the footprint. It's 2 inch by 2 inch and 3/4 of an inch, so it's roughly 50 by 20 millimeters, and the overall volume is 51 cubic centimeters. The pinout is one-to-one compatible with commercial OCXOs, so it's a drop-in replacement solution for an OCXO. Actually, comparing it to an OCXO, it has, as all rubidium clocks, much better performance in terms of, say, frequency variation over temperature. The MRO operates from -10 degrees to 65 degrees with a max frequency change over this range of 4 × 10⁻⁻10. It has a short-term stability of 4 × 10⁻11, below 4 × 10⁻11 1 second. And more importantly, when comparing to the OCXO solution, it has an aging which are at 5 × 10⁻12 per day. Again, a few orders of magnitude better than the OCXO. We've designed the MRO for low power consumption for portable battery-operated applications. It has a power consumption at room temperature below 400 milliwatts at 3.3 volts. So if we look inside the MRO, it's a block diagram form here. We usually divide the clock in 2 packages, the physics package here in blue and the electronics package in green. If we take the physics package first, I'll just really show you what are the elements inside. It's a vertical cavity source emitting laser, infrared low power laser. It's attenuated by an optical filter, passes through a rubidium cell with a microwave antenna, and is picked up. The light is picked up on a photodiode, silicon photodiode. There are also 2 Helmholtz coils to generate a bias magnetic field. On the electronics package side, you have on the lower left, you have the 10 megahertz output for the end user, which is phase locked to a 3 gigahertz VCO injected into the physics package, and the photodiode signal is returned to the electronics package and processed within the microcontroller. The microcontroller, as discussed before, closes the loop and adjusts the frequency. So in terms of pinouts, besides the 10 megahertz output on the left, you have on the right the possibility for manual frequency adjustment. You have a pin for manual frequency adjustment. You have your supply power pin. You have a pin for the monitoring the locking of the clock, and you have 2 pins for serial communication with the atomic clocks, allowing you to have readout telemetry, and you can also do a digital frequency adjustment of the atomic clock. So let's look inside first the physics package and then the electronics package. The physics package shown here, CAD design. To reduce power, we have replaced our classical plasma lamp, rubidium lamp, with a low power VCSEL. That's a power reduction of a few watts to a few milliwatts. Also, we've reduced the size of the vapor cell to 5 millimeter, which drastically diminishes the size of the physics package, but it also allows to give a relative good thermal isolation of the vapor cell, thus reducing the power consumption of the rubidium cell. To reduce the power consumption even further, we encapsulate the whole physics package in a DIL 14 standard industrial package, which is backfilled with xenon to reduce the thermal conductivity by convection and conductivity. We use, as already mentioned, the 3 gigahertz clock transition in 85 rubidium. The D1 line is infrared optical wavelength, 795 nanometers. And we use this microwave antenna microwave optical double resonance technology. If we look inside the electronics package, you recognize the photo on the right. We have done several things to reduce volume and power consumption. We use a quite simple and low power COTS components throughout the electronics package. As mentioned, the shown here in purple, the TCXO is phase locked by n fractional PLL to the 3 gigahertz VCO. And we have several of the usual analog functions in an atomic clock have been replaced by signal processing in a low power microcontroller. So this includes typical servo loops controlling the VCSEL temperature and the vapor cell temperature. They're both stabilized at roughly 75 and 85 degrees. There's also the control of the VCSEL wavelength locked to the rubidium absorption line. And of course, the microprocessor also controls the disciplining of the crystal oscillator to the atomic resonance. Okay, now the final slides I would like to show you are on the performance of the MRO50. On the first slide, you see the phase noise at 10 megahertz as a function of frequency offset from that 10 megahertz carrier. The green line is the specification, datasheet specification. And you can recognize on the plot, if you look at roughly a few hertz, 3 hertz, you see the clock servo. So that's actually the tau, this disciplining time constant that I mentioned on the very first slide. So for time scales and dynamics that are much faster than 3 hertz, so above 3 hertz, the phase noise is dominated by the LO crystal, the TCXO crystal. That's actually the black curve that you see here. That's our phase noise of the TCXO. And for time scales and frequencies, for longer time scales, that means frequencies below 3 hertz, phase noise is dominated by the atoms in the rubidium. So those behave typically, they have a white FM noise, 20 dB per decade. As I mentioned already, frequency aging is a very important parameter for holdover in TAP applications. The graph here shows total of 3 months of data with a sampling time of 70 seconds. And when you do a linear fit to this frequency of the MRO over 3 months, you get a frequency drift of 1 × 10⁻12 per day. The datasheet has a specification of ±5 × 10⁻12 per day. Moving on to time scales from 1 second to 100,000 seconds, that's 1 second to 1 day. We typically have a short-term Allen deviation, which is plotted on the graph to the left. At 1 second, we have 3 × 10⁻11. The data sheet specification is better than 4 × 10⁻11 at 1 second. And so it integrates as a tau minus 1/2 down to 10 to minus 12, slightly below 10 to minus 12. So at 100 seconds, you would have 10 times better performance. So you have roughly 2 10 to minus 12 at 100 seconds. At 1 day, the Allen deviation is 4 to minus 12. And on the graph to the right, with the same data, we plot the holdover time stability of the MRO 50. So up to 1 day, we have holdover performance of time error of only 200 nanoseconds. And I should mention that the data for these two plots is sampled over 10 days with a sampling time of 1 second. And that particular MRO unit had a drift of 1.5 10 to minus 12 over these 10 days. So I finish my talk and I give the word to Jean-Arnaud.
Thank you, Christian. So a few words on the Orolia time card. You might have read in the news and in the Facebook blog that we are working with them on implementing that MRO50 on a PCI Express card. That's not something new, having PCI Express timing card, but what is new is that we can now, with the size, weight, and power of the MRO50, have the rubidium directly soldered on a board. So please go on next slide.
Christian, I have one question here on your time card. So, as probably most of you know, the time card specification is now approved by the OCP committee, and you guys are now welcome to contribute this device into the OCP marketplace. So yep. This is a call for you to go ahead and submit that into the marketplace. That can be either as a inspired or as a accepted OCP product.
That's what we are doing at the moment. I was discussing with the OCP guys this afternoon, so we are filling up the papers, and the time card will be very soon in the marketplace. So awesome. that's why we take the opportunity to describe it right now.
That'd be great. Looking forward to see out atomic reference time on the marketplace. Thank you.
You're welcome. So yeah, can you click, please, Christian? So the change in paradigm here is that instead of having a standard PTP networks with switches with PTP enabled switches in all the network, what is this time card gives you the possibility to have timing directly on each and any servers with a very high accuracy, because as Christian mentioned, we can reach sub-microsecond holdover performance with this time card. So I'm going a bit fast on this one, but just to give people a time for question. But that's mainly it's changing the paradigm from having grandmaster in the network that distribute the time, and then even with PTP-enabled switches, will add some errors in the timing. Here, you can have directly time distributed to your application or DB servers or whatever, where you need most the timing. Next, please, Christian. So what it is, it's so as Ellen mentioned, it's fitting the need described in the OCP specification for a time card. So it's a PCI Express X4 format with the MRO50 on board, obviously, and we have also implemented the latest timing receiver from uBlocks directly on the board. And the rest is mainly software. We'll see that in the next slide, but mainly software driven. And yes, it is open source, and I can I've put the link to our repository where you can see all the files, all the design files, the FPGA firmware, and everything you need to understand better the time card. So yes, next slide, please. So as I said, what we did is that we put the minimum in the hardware, the minimum in the FPGA, because we want to fight also a bit the obsolescence of the hardware. So we want to be able to change the hardware very quickly. Should we have the need for a new FPGA, for a new receiver, or for new generation of the clock? We don't want to have to redesign everything and to port all the functionality into hardware. So most of the functionalities are done in software. Software is open source, and the only thing that we do in FPGA is the phase meter and a PCI Express to serial communication. All the devices on the board, everything communicates through the PCI Express bus for the sake of simplicity. So really, what we want to achieve here is that the main part is done by you. All the software package you need to run the hard card are open source, and using the common driver that is being developed as we speak. And the day you want to change the card, you want to have a new card, you don't have to change everything. Next slide, please. Back to you, Stavros.
Sorry, guys. Can I have a quick question?
Yeah.
Do you mind?
Sure.
No. So if you can go back to the previous slide.
Yeah.
So it says that the serial is exposed in GPS in NMEA format. Is that right? Because I thought you wanted to provide the leap second information, etc. And from what I remember, the NMEA doesn't have it.
It's not only NMEA. You're right. It's a full serial link, so we put whatever we want. Here we are using NMEA plus the uBlocks protocol, but it could be any protocol. That's just a path through the GNSS receiver, and we have our own daemon that manage the leap second, for instance, and implement that into the PHC. Is that okay?
Yeah. So you are not using NMEA, if I understand correctly, in the real world, let's say.
No, not really. We can have NMEA if we want.
But then you're missing leap second information.
Yeah, that's right.
So is it UBX?
Yeah.
Okay, cool. Thank you.
So next slide.
Yes. So actually, this is just our last slides for open, and then we can open for questions right now. I just saw out of the corner of my eye that the Stavros left the meeting. He had to go earlier, so I think I will give back the word to the organizers and open for questions with regard to this presentation.
Okay, can have one question then. If we could go back to the photo of your time card, I'd like to ask about the additional power supplies, power connectors on it. Are they for backup power or they are for just cleaner power from your PSU?
That's just if you want to power the board on the table outside of a computer. Due to the consumption of everything on the board, we don't need additional power. But if you want to use the board on a table, you can, and we have that additional power for that.
Mm-hmm. Maybe then in like future release, it would be good to add some independent interface like a USB connector or something like that, so that you can use it outside of PCI.
Yeah, sure. We have a JTAG on it, obviously. Yeah, we could think about having something more 2021, I guess.
Yep. And also, yeah, is backup power something that would benefit time cards, or it's not really very useful for them?
No, it's not really useful in large scale production. We even think about removing them because it might be needed for some testing and debugging. This is one of the prototype cards, but for day-to-day usage, I'm not sure. So we may DNP the connectors. So that's still being think at the moment.
Yeah, but my question was rather, whether adding such connector for dedicated battery power backup or something like that would be useful, or it's totally just a waste of.
No, it's not useful.
Okay.
Really, no.
I think, sorry, like what like initially why I had the connector was I was thinking that, say, if you have like some power surge or something, like let's say your server goes down for, I don't know, 5 minutes or something, comes back, you don't want to lose, let's say, the holdover and like all this disciplining that you had, that it took, let's say, 24 hours. So that was why we had it initially. But as we're going forward, like, really depends on how the applications will end up like defining things. I don't know, John Paul, do you want to add anything to it?
Yeah. The goal of this time card is also to be installed as quickly as possible without any additional wiring inside the box. So yeah, we'll see. Maybe we'll keep it, but really it's not needed in day-to-day usage. So it could be a backup solution, yeah, at some point for maintaining the rubidium under power. But yeah, let's see.
Yeah, because just like Ahmad said, like keeping your holdover during reboots or things like this may be good idea, right?
Yeah, you're right.
That's a lot of complexity, like you have to have an independent power source, and which means you probably have to have a power supply in the rack connected to different sources. So sounds like theoretical idea sounds very good. I don't know how practical this is.
I believe you can solve this with a battery that would just keep it during this time, like in the RAID controllers or something like this.
Yeah, like the HP servers, they have this battery pack that is mainly designed for this kind of things, and it's actually a 12-volt rail. They feed it into like the storage devices, and it keeps them up. And this was literally that connector and everything was just designed for that purpose. But in our design, we just took it off. Like again, there's one that we have, let's say, for deployment data center or whatever, and there is the one that's on the website. So if anyone needs it, there are other ways you can bring it back. But how the design was, like basically having this connector was, it was mainly to just keep up the FPGA and the atomic clock running, so they like you're still at the same state.
And what is the power consumption roughly of those two?
So I mean, it depends on the atomic clock. So the one here Orolia has is, I'm assuming it's like a milliwatt thing. The SA53 is in range of, I think, 4 or 5 watts. Like we have Robert Lutwak here. He can correct me if I'm wrong. And then if you use, let's say, a CSAC, you go back again in the same world of what the Orolia one is. It's like all milliwatts.
Okay.
Yeah, the clock is around 300 milliwatts. And the rest doesn't consume so much. So we didn't measure it at the moment, but it's something around one watt maximum. So really, you don't, you're more than okay with the PCI Express power supply.
I have another question. Looking at the schematics and photos on the Orolia Art Card version 3 on the Orolia website, it looks like you have footprints for 6 different oscillators at the location of the MRO50. Can you tell us what 6 oscillators you have footprints for?
That's the standard behavior. When we do a design, we always add the common footprints we use just in case, really. So I don't know if we will one day implement those, but generally we have footprints for the standards VCXO formats, and we should have the pads also for the TCXO. I don't know if that's survived, but yeah, we generally put that because it doesn't cost much, and it prevents us from rerouting should we want to make a different version.
So I see TCXO, and I assume the MRO50, the CSAC, and the SA31.
Yeah.
So I'm wondering what the other 2 are.
That should be the size of the VCXO we are using.
Okay. So the other 2 are OCXOs?
Yeah. We generally use 2 size of VCXOs. So.
Okay. Thank you.
Okay. Any other questions before we wrap up? Looks like we are on time. Well, maybe someone may wonder, like, so what's the status if someone wants to buy these cards? Like, is the price determined? Is it available? Is it any of the following? Like,
Yeah, we are still making prototypes as we speak and beginning the industrialization. So we start answering the RFPs and our RFIs around the card. So if you have any quantities, if you have any interest in this card, you can contact us. We'll put you in the list. That's also important for us, that understanding the market and whoever needs and wants that kind of cards. So yeah, do not hesitate. Soon, as I said, with Elad, we will be in the OCP marketplace. So all those data, price, lead time, and so on will be available very soon. I can't answer tonight, unfortunately, but that's coming very soon.
Okay, so I think we can
can't
wrap
hear
up.
you.
I guess the answer would be to reach out to Orolia until it's available on the OCP marketplace.
Yes, correct.
Perfect.
Okay, so let's wrap up.
Thank you, everyone. Thank you, the Orolia team, for an amazing presentation.
Yeah, thank you.
Thank you.
you.
Bye.
Thank you, guys.
Bye.